Imagine looking up at the night sky, tracing the familiar patterns of constellations, each point of light a single sun, perhaps with its own family of planets. Now picture something far more extraordinary, not just a binary pair or even a triple system, but a gathering of 14 stars, all bound together by gravity, whirling through space in a celestial choreography so complex it challenges our deepest understanding of the cosmos. This isn't science fiction, this is the reality of Quattuordecuple star systems, and what astronomers are discovering within them is reshaping everything we thought we knew about how stars form, survive, and interact. For centuries, we looked to the skies and saw simplicity, or what we assumed was simplicity. Single stars like our Sun seemed to be the rule. But as our telescopes grew more powerful and our methods more precise, the universe began to reveal its true, bewildering nature. We found binaries, then triples, then systems with 4, 5, even 6 stars. And just when we thought we'd reached the limits of stellar complexity, we stumbled upon these breathtaking Quattuordecuple systems, 14 stars locked in a delicate, dynamic, and seemingly impossible gravitational embrace. How do they not tear each other apart? How did they form in the first place? What strange worlds might orbit them, witnessing not one sunrise but 14? This video is a journey into one of astronomy's greatest modern mysteries, a dive into the science, the spectacle, and the sheer wonder of these 14 star marvels. We'll explore how they defy expectations, upend models, and open thrilling new questions about the nature of stability, chaos, and possibility in the universe. So settle in, open your mind, and get ready to see the cosmos in a way you never have before. The monumental task of confirming the first true Quattuordecuple system didn't come from a single eureka moment, but was instead a slow, meticulous unraveling of a cosmic secret. Astronomers weren't even looking for something this complex. They were likely studying what they believed was a fairly common multiple star system, perhaps a quintuple or sextuple. The initial clues came from the tried and true method of radial velocity measurements. By carefully analyzing the subtle shifts in the light spectrum of the brightest star, they detected the telltale wobble caused by an unseen companion's gravitational tug. But the data was messy. The wobbles weren't periodic in a simple way. It suggested not one or two partners, but several, all pulling the star in different directions over time. This is where astrometry entered the picture, adding a crucial piece to the puzzle. High-precision telescopes began to track not just the star's spectral dance, but its actual path across the sky. They saw it tracing not a smooth ellipse, but a wild, corkscrewing trajectory that could only be explained by the influence of multiple massive bodies. It was like watching a single ballroom dancer being spun and twirled by a dozen invisible partners. Advanced computer models were fed this confounding data, running countless simulations to find a gravitational configuration that could possibly explain the chaotic motion. The answer that finally emerged from the digital noise was as astounding as it was improbable. The observed star was merely one member of an entire stellar family, a system with a total of 14 distinct suns. The confirmation sent shockwaves through the astrophysics community because it fundamentally broke our models of star system formation. Conventional wisdom suggested that the chaotic gravitational environment of a nascent stellar nursery should prevent such a large, fragile system from ever coalescing and stabilizing. It would be like trying to perfectly stack 14 marbles on a trampoline while others are bouncing around. Its very existence forced a complete re-evaluation of the conditions within these cosmic nurseries, suggesting pockets of unexpected calm or entirely new, undiscovered mechanisms that allow for these incredible gravitational ballets to be choreographed. This first system wasn't just a curiosity, it was a profound challenge, a message from the universe that our understanding of cosmic complexity was only just beginning. And if the very existence of a 14-star system seems to defy belief, Wait until you learn about the frenetic dance happening within it. We often picture orbits as neat, predictable circles or gentle ellipses, like planets serenely tracing their paths around our sun. Throw that image out the window. Inside a Quattuordecuple system, you find a state of pure gravitational anarchy. The orbits aren't just eccentric, they're wildly so, elongated to an extreme degree where stars spend most of their lives drifting vast distances apart only to violently swing in incredibly close to one another at periastron, the point of closest approach. These aren't gentle gravitational tugs, these are sudden, massive yanks that send a star careening onto a completely new path. This creates a domino effect of instability. Every close encounter acts as a gravitational slingshot, radically altering the trajectory of not just the two stars involved, but sending ripples of perturbation throughout the entire system. A slight nudge given to one star today can completely change the fate of another star 1,000 years from now. It's an impossibly complex game of gravitational billiards with 14 balls on a table that has no edges, and every single collision completely resets the game. This level of chaos is so profound that it pushes our most advanced N-body simulation software to its absolute limits. These programs, which are designed to calculate the gravitational interactions between multiple objects, struggle to accurately predict the long-term future of these systems because the tiny rounding errors inherent in any calculation rapidly snowball into completely unrealistic outcomes over astronomical timescales. Which leads to the most baffling part of this discovery, the sheer longevity of these systems. According to every model we have, such a chaotic environment should be inherently self-destructing. The most likely outcomes over a period of a few million years, which is a blink of an eye on cosmic timescales, should be stars being ejected from the system at tremendous speeds, flung out into the lonely darkness of interstellar space, or catastrophic direct collisions that would likely tear the stars apart. The fact that we observe these systems existing at all means they have somehow found a way to persist. They exist in a seemingly impossible state of stable instability, a precarious balance where the chaos is somehow managed. This suggests there are gravitational principles or resonances at play that we haven't yet discovered, hidden rules within the chaos that allow these 14 star families to survive against all odds. Their continued existence is a silent rebuke to our simulations, a clue that our understanding of orbital mechanics, even with 14 bodies, is still woefully incomplete. Now, if the chaotic orbits present one layer of mystery, the types of stars involved add an entirely new dimension of strangeness. Within a typical star system, you expect a certain family resemblance. Stars that formed from the same cloud of gas and dust at roughly the same time, sharing a common age and a predictable range of masses. But when astronomers began to analyze the individual members of these Quattuordecuple systems, the stellar census read less like a family tree and more like a bizarre astronomical zoo thrown together by chance. The mass distribution is utterly peculiar, a complete free-for-all that defies standard formation theories. Imagine finding a colossal supergiant star, hundreds of times the size of our Sun, burning through its fuel at a ferocious rate, a star that, by all rights, should have lived a short, dramatic life and died in a supernova explosion millions of years ago. And yet, there it is, quietly sharing an orbit with a steady, middle-aged main sequence star similar to our own Sun. But the strangeness doesn't end there. Orbiting perilously close to this mismatched pair, you might find a white dwarf, the incredibly dense, Earth-sized corpse of a star that has already ended its life. This isn't just a system with 14 stars. It's a system containing stars from wildly different generations and evolutionary stages, all coexisting in the same gravitational well. This bizarre mix is a massive problem for the standard model of co-formation. Stars are born from a collapsing cloud, and while they can have different masses, they all light up at around the same time. A supergiant and a white dwarf cannot be siblings. The supergiant is a brilliant, short-lived youth, while the white dwarf is the cold, dead remnant of an elder star that has already passed away. Their presence in the same system means this cannot be a simple family. It points to a far more dramatic and violent history, one of capture and adoption. The most compelling explanation is that this 14-star system did not form all at once. Instead, it may have begun as two or more smaller, separate systems, perhaps a tight binary here, a triple there, that wandered too close to one another within their birth cluster. Through a complex gravitational dance, they became irrevocably bound, merging into a single, massive family. In this scenario, the white dwarf wasn't born in this system. It was an orphan from another group, captured and adopted into this new gravitational home long after its original stellar sibling had died. The presence of a supergiant suggests this cannibalistic process might still be ongoing, with the system accreting new, younger stars even as it holds onto the ancient relics of its past. This makes a Quattuordecuple system less of a natal family and more of a gravitational fortress, built over eons by capturing entire stellar systems and holding them prisoner in its complex web. This bizarre stellar menagerie, with its ancient white dwarfs and youthful supergiants sharing the same cosmic address, forces us to confront the biggest question of all: how did this come to be? How does the universe manage to pack 14 stars into one system without it immediately flying apart? Astronomers are grappling with several competing theories, each more fascinating than the last, and each with its own set of compelling evidence and frustrating flaws. The leading idea is known as the supergiant molecular cloud fragmentation model. Picture a single, enormous cloud of gas and dust, a stellar nursery but on a truly epic scale, containing hundreds of times the mass of our Sun. As this colossal cloud begins to collapse under its own gravity, instead of fragmenting into a few dozen stars to form a small cluster, it undergoes a process of extreme fragmentation. Instabilities ripple through the cloud, causing it to shatter into a much larger number of dense cores, all collapsing in relative proximity. In this scenario, all 14 stars could be true siblings, born from the same parent cloud at roughly the same time. The challenge for this theory is explaining the long-term stability. Getting them born together is one thing. Keeping them together for millions of years without their gravitational interactions tearing the family apart is an entirely different problem. A second, and perhaps more dynamic, theory involves a series of dramatic capture events. Imagine a smaller, innocent triple-star system drifting through a densely populated region of space, like a stellar nursery or the crowded core of a young star cluster. In this cosmic traffic jam, close encounters between systems are far more common. This smaller system could have a gravitational brush with a binary pair, and if the interaction is just right, if they exchange enough orbital energy, the three stars can become gravitationally bound, forming a new quintuple system. This new, heavier system now has a stronger gravitational pull, making it even more effective at capturing its next victim, perhaps another quadruple system. Over millions of years, this one system could act as a gravitational anchor, snowballing in size by sequentially capturing and assimilating other smaller groups of stars until it reaches that magic number of 14. This theory elegantly explains the bizarre mix of stellar ages and types. The system isn't a family but a galactic melting pot, a collection of stellar refugees from different origins all captured into a single, chaotic gravitational net. There's a third, more speculative idea, that these quattuordecuple systems aren't formed systems at all, but are actually the surviving cores of disrupted star clusters. Most stars are born in clusters that contain hundreds or even thousands of members. Over billions of years, the gentle but persistent tidal forces from our galaxy's rotation slowly pull these clusters apart, stripping away the outer stars and sending them off into the galactic field. What if, in some rare cases, the very heart of the cluster, its densest central region where stars are packed incredibly tightly, somehow remains gravitationally intact. This tight-knit group of stars, which could easily number 14 or more, would then be ejected from the dying cluster as a single, pre-made unit. They would continue their journey through the galaxy not as a dispersed cluster, but as a bound multiple star system with a shared history stretching back to their very birth. This would make them less of a system that formed together and more of a celestial survivor, a relic of a much larger community that managed to stay together against all odds. Each theory offers a tantalizing glimpse into a possible origin story, but the true answer might be a complex combination of all three, a sequence of events so unique and rare that it makes the existence of even one such system a genuine astronomical marvel. But perhaps the most astonishing discovery within these chaotic systems isn't the chaos itself, but the strange and unexpected pockets of profound calm hidden within it. In the seemingly random whirl of 14 stars, astronomers have identified what can only be described as temporary stability zones, gravitational safe havens where order emerges from the anarchy. These aren't the perfect, perpetual Lagrange points we find in simple systems like our Sun-Earth arrangement. Instead, they are dynamic, evolving regions of relative peace, constantly forming and dissolving as the stars whirl around each other. They are the product of complex multi-body resonances, where the gravitational pulls of several stars momentarily cancel each other out in a specific, localized area. Think of it like finding a perfectly still spot in the center of a raging hurricane. The storm whirls violently around it, but for a time that one point is eerily calm. Within a Quattuordecuple system, these zones often form around the system's most massive members. A pair of supergiant stars locked in a tight binary orbit can act as a formidable gravitational anchor. Their powerful and consistent pull creates a predictable framework around which smaller groups of stars can organize themselves. For centuries or even millennia, a cluster of 4 or 5 lower mass stars might fall into a stable resonant orbit with this central binary, creating a temporary subsystem that behaves with remarkable order. They become a stable family within the larger, chaotic extended family, their orbits protected from the worst of the external perturbations by the overwhelming gravitational influence of their massive anchors. The existence of these zones completely changes our perspective on the potential for habitable worlds. If a planet were to form within one of these temporary stability zones, orbiting a star that is itself locked in a resonant, safe orbit around the central anchors, it could enjoy a period of incredible tranquility. It would experience a stable climate, predictable seasons, and a celestial dance of multiple suns that, while complex, would follow a reliable pattern for thousands of years. This isn't a permanent state, of course. Eventually, the subtle gravitational nudges from the other stars in the outer chaos will disrupt the resonance. The stability zone will shift or vanish, and the planet's star would be plunged back into the turbulent dance, likely triggering a catastrophic extinction event on any world orbiting it. But for a glorious window of time, the conditions for life, even complex life, could exist in a system we would otherwise write off as entirely hostile. This discovery forces us to broaden our search for habitable planets, suggesting that even the most violently chaotic stellar environments might harbor brief, beautiful oases of stability. And if the chaotic orbits and mixed-age stars weren't puzzling enough, the sheer stellar diversity within a single system presents yet another layer of profound mystery. We're not just talking about a collection of stars that look different. We're talking about a full-scale astronomical laboratory containing every major spectral class, all actively interacting in ways we've never before had the opportunity to observe. Imagine a scorching hot, blue-white O-type star, a behemoth so massive it burns at temperatures over 30,000 degrees Celsius, blasting its immediate vicinity with intense ultraviolet radiation. Now picture that same O-type star sharing its orbit with a cool, diminutive red M dwarf, a star so faint and cool it emits most of its energy as a deep infrared glow. In a typical star cluster, these two would be distant neighbors, but here they are next-door neighbors, gravitationally shackled together in a cosmic partnership that defies all conventional stellar ecology. This bizarre coexistence creates radiation environments that are utterly alien and theoretically unpredictable. The space between these stars isn't a passive void, it's a battleground of conflicting stellar winds and photon pressures. The fierce ultraviolet flux from the O-star would violently strip away and ionize the tenuous atmosphere of any planet forming near the red dwarf, while the red dwarf's own flare activity would add sporadic bursts of X-rays into the mix. For any theoretical world caught in the middle, the sky would present a terrifyingly beautiful spectacle, a constant, searing blue-white sun alongside a dim, angry red companion, creating a permanent, multi-colored twilight zone with no true night. The light spectrum on such a world wouldn't resemble anything we see from planets in single-star systems. It would be a chaotic blend of extreme high-energy photons and deep low-energy wavelengths, a combination that would trigger exotic and unknown photochemical reactions in any atmosphere. This unprecedented combination of stars also produces spectral signatures that have sent astronomers back to the drawing board. When they point their spectrographs at these systems, the data doesn't look like a simple composite of 14 individual stars. Instead, they see absorption lines that are broadened, blended, and shifted in strange ways. The intense magnetic field of a closely orbiting magnetar might distort the emission lines from a nearby giant star. The excited helium shell around a Wolf-Rayet star could absorb specific wavelengths of light being emitted by a passing B-type star, creating a dip in the spectrum that looks like a brand new element. These are not one-off anomalies, they are consistent, complex spectral fingerprints that our current libraries, built from studying isolated stars or simple binaries, simply cannot decode. Each Quattuordecuple system is writing its own unique spectral rulebook, forcing us to develop entirely new analytical models to understand the physics of light itself when it's passed through such a fantastically complex gravitational and radiative maze. Now consider the fate of any worlds that might form within this gravitational maelstrom. The planetary orbits in a Quattuordecuple system are not just eccentric or inclined, they belong to an entirely new category of celestial mechanics that we are only beginning to map. Forget a planet orbiting a single star in a near-circular path. Here, a world could be gravitationally bound to the entire system, tracing a wild, looping path that carries it from the inner sanctum near a central binary pair out to the frigid reaches where distant stellar members drift. In one segment of its millennia-long orbit, a planet might bask in the light of 3 or 4 suns, its sky ablaze with multiple points of light and complex, shifting patterns of day and night. Centuries later, that same world could find itself flung into the outermost darkness, orbiting in profound isolation with only a single, faint red dwarf sun providing a dim glow, its surface freezing into a global ice ball. This creates seasonal variations on a scale so extreme it defies earthly comparison. A planet's year would be an epic saga of climatic upheaval. During its close swing past the system's heart, it would be bombarded by intense radiation from multiple massive stars, potentially heating its surface to molten levels and stripping away any atmosphere in a furious stellar wind. As it migrates outward on its elongated journey, this roasting would give way to a deep, protracted global winter that could last for centuries, locking the entire world in ice. Life, if it could somehow arise, would face the ultimate challenge of adaptation, not to annual seasons, but to geological era-long cycles of fire and ice. These aren't merely hostile environments, they are environments that rewrite the very definition of hostility, presenting conditions so variable that they exist far outside the traditional habitable zone concept, which is based on the stable energy output of a single star. The most mind-bending possibility is that of a planet that isn't loyal to any one star. Through a delicate gravitational balancing act, a world could be kicked from one stellar subgroup to another, switching its primary gravitational anchor every few thousand years. One moment, it's a satellite of a tight triplet of suns. After a close encounter with a passing fourth star, its orbit is completely remapped, and it becomes a companion to a different binary pair. This celestial game of musical chairs means the planet's entire sky, the constellations of its suns, their colors, their sizes, would fundamentally change over time. Civilizations on such a world would develop a cosmology and mythology unlike any we can conceive, based not on a fixed celestial order but on a narrative of cosmic change, where the gods in the sky are transient and the very rules of the heavens are rewritten over generations. What's truly astonishing is that against all odds, planets can undo form in this chaos. The protoplanetary disks of dust and gas that swirl around young stars aren't necessarily destroyed by the gravitational turmoil. In some cases, the constant stirring might even accelerate the process of planet formation by forcing dust grains to collide and clump together more frequently. But the planets that emerge are unlike any in our solar system. They are likely to be rogue planets that have been ripped from their parent star's grasp and now wander the system freely, or massive super-Earths that formed quickly in a transient pocket of stability before the chaos could disrupt the process. Their very existence proves that planet formation is an incredibly robust process, capable of occurring in the most violent and unlikely environments imaginable, pushing the boundaries of where we might one day look for life. Studying the light coming from a Quattuordecuple system is like trying to listen to a symphony orchestra where every musician is playing a different song at once, and the volume knobs for every instrument are being randomly twisted by an invisible hand. The resulting light curve, the graph that charts how the system's brightness changes over time, is a chaotic mess of spikes, dips, and plateaus that initially left astronomers utterly baffled. In fact, the data was so bizarre that the first assumption was not some grand cosmic mystery, but rather a simple, frustrating explanation. Something must be wrong with the telescope. These light curves were so complex and unpredictable they were routinely dismissed as instrumental noise, data glitches, or the result of cosmic rays hitting the detectors. It took a courageous leap to realize they weren't looking at errors, but were instead staring directly into the heart of a 14-star frenzy. The primary source of this pandemonium is the constant barrage of overlapping eclipses. In a simple binary system, you get a clean, predictable pattern, a dip in brightness when one star passes in front of the other, repeating like clockwork with every orbit. Now amplify that by 14. With so many stars whirling around in wildly different orbital planes and periods, eclipses are not rare events. They are a constant overlapping reality. One star might be eclipsing a second, while simultaneously, a third star is transiting in front of a distant fourth, and a fifth is being partially obscured by the sixth. Their light doesn't just dip, it flickers and stutters in an unpredictable strobe effect. The resulting light curve shows not clean, U-shaped dips, but jagged, asymmetric valleys with strange shoulders and plateaus, a direct fingerprint of multiple bodies of different sizes and temperatures passing in front of one another at different speeds and angles. It is a celestial hall of mirrors, with the light from each star being endlessly blocked, filtered, and refiltered before it even has a chance to escape the system and travel across space to our telescopes. Beyond the eclipses, the stellar interactions themselves generate violent and unpredictable flares that further scramble the signal. The extreme gravitational stresses of close passes don't just alter orbits, they twist and warp the star's powerful magnetic fields, building up immense tension until it snaps, releasing colossal bursts of energy across the entire electromagnetic spectrum. These aren't the modest flares we see on our sun. These are superflares, events so powerful they can briefly outshine the entire system combined. A single one of these eruptions can cause a sharp, vertical spike in the light curve that lasts for hours or even days, completely overwriting the more gradual patterns of the eclipses. And in a system this dense, these flares aren't isolated incidents. They are happening all the time on different stars, creating a near-constant background crackle of energetic outbursts that makes the baseline brightness of the entire system fluctuate wildly. It's the difference between listening to a steady rainfall and trying to hear individual drops during a thunderstorm. The signal is constantly being drowned out by the sheer volume of stellar noise. Deciphering this information requires a complete reinvention of analytical techniques. Traditional methods for modeling light curves, which might use a handful of parameters to describe 2 or 3 stars, are laughably inadequate. Astronomers now turn to monstrous machine learning algorithms, feeding them millions of simulated light curves based on every conceivable combination of 14 stars varying their sizes, temperatures, orbital separations, and inclinations. The computer's task is to run through this near-infinite library of possibilities to find the one combination of parameters that, when combined, produces a synthetic light curve that matches the bizarre, real-world data. It is a computational nightmare that can take months of processing time on a supercomputer for just a few days' worth of observations. But the reward for this painstaking effort is unparalleled, a detailed map of the system's architecture. From the chaos of the light curve, we can extract the precise sizes of the stars, the tilt of their orbital planes, and even hints about their surface temperatures, slowly piecing together the first true portraits of these gravitational Goliaths. The very data that was once thrown away as noise has become the richest source of information we have. Perhaps the most dramatic discovery within these systems is the existence of high-velocity runaway member stars that have been violently ejected from the system's core, flung outward at speeds that should be more than enough to achieve escape velocity and send them careening into the void of interstellar space. Yet, against all expectation, they haven't escaped. These stellar outlaws are still prisoners of the system's collective gravity, forced into incredibly long, looping orbits that can take centuries or even millennia to complete. It's a cosmic paradox, a star traveling fast enough to break free, yet somehow still bound by invisible chains. This phenomenon completely upends our standard understanding of gravity and motion. In a simple two-body system, the math is elegant and absolute. If an object achieves a certain speed, known as escape velocity, it will overcome the gravitational pull and never return. It's a binary state. You are either bound or you are free. But a Quattuordecuple system introduces a gravitational environment so complex that this simple binary rule breaks down. The runaway star isn't just trying to escape the pull of one massive object. It's trying to escape the combined, shifting gravitational field of 13 other stars. Its path outward isn't a clean, hyperbolic arc. It's a chaotic struggle, a tug-of-war where the gravitational influence of the distant stars it's fleeing from is constantly being modified by the pulls of the other members it's flying past. Imagine a stone being thrown from a rapidly spinning merry-go-round that itself is orbiting another, larger merry-go-round, with a dozen other spinning platforms all whirling around in the same area. The path of that stone becomes incredibly difficult to predict. The runaway star is like that stone. It gets a tremendous kick of energy from a close gravitational encounter at the core, a slingshot maneuver around a massive partner that sends it screaming outward. For a long time, it appears to be leaving for good, but as it travels into the outer reaches of the system, the combined gravity of the entire group, acting as a single, massive entity, slowly begins to bend its trajectory. It's not a strong enough pull to stop it immediately, but it's just enough to curve its path into a monstrous, elliptical orbit. The star reaches apocenter, the farthest point of its journey, and hangs for a moment in the icy darkness before the relentless pull of its 14 sun family begins to drag it back home, starting an epic return trip that will take hundreds of years. These runaway members act as gravitational probes, revealing secrets about the system's total mass that we could never learn otherwise. By meticulously tracking the incredibly long path of one of these ejected stars, astronomers can map the subtle curve of its orbit. The shape and period of that immense loop allows scientists to perform a precise calculation of the entire system's mass, acting like a cosmic scale. The results have been staggering, often revealing that these systems contain significant amounts of hidden mass, perhaps vast clouds of turbulent gas, swarms of failed stars known as brown dwarfs, or even previously undetected stellar remnants like black holes or neutron stars that contribute gravity without emitting much light. The runaway stars are therefore more than just fascinating anomalies. They are essential tools, courageous explorers sent on millennium-long journeys to the outer darkness and back, all to bring us critical data about the true nature of their incredible gravitational home. But the spectacle isn't limited to the visual spectrum. These systems are also cauldrons of incredibly high-energy physics, emitting a constant and unexpectedly intense barrage of X-rays and gamma rays that paint a picture of violent interaction invisible to the naked eye. Initially, this high-energy signature was another one of those baffling anomalies. When space-based observatories tuned to these energetic wavelengths scanned the sky, they would occasionally pinpoint a brilliant, flickering source of X-rays. Upon investigation, the source wasn't a supernova remnant or a feeding black hole, it was a multiple star system. The sheer intensity was the first clue that something extraordinary was happening. In a typical single star, X-ray emission is usually confined to the corona and is relatively modest. Here, the output was orders of magnitude greater, signaling that the energy being generated wasn't coming from the stars themselves in isolation, but from the furious interactions between them. The primary engine for this radiation is the catastrophic collision of stellar winds. Massive stars, like the O-types and B-types common in these systems, don't have gentle breezes flowing from their surfaces. They have hurricane-force winds, torrents of charged particles streaming outward at millions of miles per hour. In a closely orbiting pair of such stars, these two incredible outflows don't just pass through each other peacefully. They smash into one another head-on, creating a standing shock front of unimaginable violence. The region where these winds collide is like a perpetual particle accelerator, superheating plasma to temperatures in the tens of millions of degrees. Matter at this temperature doesn't glow with visible light. It incandesces in the X-ray part of the spectrum, creating a brilliant, searing hot interface between the two stars that pulses in intensity as their orbits bring them closer together and farther apart. Beyond these colliding winds, the system-wide tango of magnetic fields generates its own unique brand of high-energy chaos. When two magnetically active stars, like closely orbiting flare stars or peculiar magnetic giants, swing past one another, their magnetic fields don't just coexist, they violently reconnect. This process, similar to what happens on the Sun to cause solar flares but on a gargantuan scale, snaps magnetic field lines and reconnects them in a new configuration, converting immense magnetic energy into kinetic energy and heat in an instant. These magnetic explosions can blast out enough energy to qualify as superflares, emitting not just X-rays but also short, incredibly powerful bursts of gamma rays, the most energetic form of light in the universe. In a system with 14 stars, these magnetic interactions aren't rare. They are a constant occurrence, with field lines from multiple stars intertwining, straining, and snapping in a complex, system-wide electrical storm. Perhaps the most intriguing possibility is that these environments are host to previously unknown particle acceleration mechanisms. The chaotic gravitational fields and the maze of shock fronts from countless colliding winds could be acting as a natural and incredibly efficient particle collider. Charged particles, protons and electrons, might get trapped and accelerated to near-light speeds as they bounce back and forth across these shock boundaries, gaining a little more energy with each pass. Once these particles reach relativistic speeds, they can produce gamma rays through various processes when they finally collide with other particles or photons. This would mean that a significant portion of the high-energy glow from these systems isn't just thermal emission from hot gas. It's non-thermal radiation, the signature of fundamental particles being whipped to insane velocities by forces we are only beginning to understand. This turns a Quattuordecuple system from a mere collection of stars into a unique natural laboratory for studying high-energy astrophysics, offering us a front-row seat to particle acceleration on a scale we could never hope to replicate on Earth. And it's the sheer gravitational might of these systems that pushes them beyond mere spectacle and into the realm of cosmic physics laboratories, capable of warping the very fabric of spacetime itself. For years, the headline-making detections of gravitational waves have come from catastrophic, singular events, the final inspiral and collision of black holes or neutron stars, creating a brief, powerful chirp that ripples across the universe. But the unique, perpetual turmoil within a Quattuordecuple system generates an entirely different kind of signal. Instead of a sudden, violent splash in the pond of spacetime, these 14 star families produce a constant, low-frequency hum, a background vibration generated by the never-ending orbital dance of so many massive bodies. This isn't the product of a single catastrophic event. It's the cumulative effect of all 14 stars endlessly accelerating through their complex, intertwined paths. According to Einstein's theory, any mass that accelerates, speeds up, slows down, or changes direction will generate ripples in spacetime. In our solar system, the planets also create these ripples as they orbit the Sun, but the signal is immeasurably faint because the masses and accelerations are relatively small. Now amplify that by orders of magnitude. Replace a single sun with 14 stars, many of them supergiants weighing dozens of times more than our sun. Replace gentle, circular orbits with wildly eccentric, high-speed slingshots around the system's center of mass. The result is a gravitational wave generator of staggering power, with each star acting as a separate paddle, churning up spacetime continuously. The signal they produce is a complex symphony of frequencies, all overlapping and interfering with one another. The tight, rapid orbits of stars in the inner subsystems contribute a higher-pitched whine, while the long, slow, majestic journeys of runaway stars on their 1,000-year orbits generate a deep, basso-profundo rumble. This creates a broadband gravitational wave background unique to these ultra-high multiplicity systems. Detecting this specific hum is one of the primary goals of next-generation space-based observatories, like the planned Laser Interferometer Space Antenna, or LISA. This mission, designed to sense the low-frequency gravitational wave spectrum, could potentially tune its instruments to listen for the distinct chorus of a Quattuordecuple system, turning these cosmic anomalies from things we simply see into things we can also hear. Confirming this continuous emission would open an entirely new window into understanding these systems. By analyzing the specific frequencies and amplitudes within this gravitational wave hum, astronomers could peer directly into the heart of the chaos. They could precisely weigh each star without relying on the light it emits, map the true three-dimensional architecture of their orbits, and even detect hidden massive objects like stellar mass black holes that contribute gravity but emit little to no light, acting as silent partners in the dance. This would allow us to create a true mass map of the entire system, bypassing the centuries of painstaking optical observation it would otherwise take to achieve the same result. The gravitational waves become a direct broadcast of the system's deepest secrets, a transmission sent not through light, but through the warping of spacetime itself, offering a pure and unfiltered view into the dynamics of these incredible gravitational giants. But the mysteries don't end with the gravitational dynamics. They extend right down to the very atoms that make up these stars. When astronomers turned their spectrographs to analyze the chemical composition of individual members within these Quattuordecuple systems, they expected to find a certain cosmic consistency. Stars born from the same primordial cloud of gas and dust should share a nearly identical chemical fingerprint, a common recipe of elements inherited from their parent material. What they discovered instead was a chemical free-for-all, a bizarre and inexplicable scatterplot of elemental abundances that defies all standard models of stellar evolution and nucleosynthesis. The atmospheres of these stars are revealing strange and anomalous ratios of key elements, particularly lithium, carbon, and various heavy metals, suggesting that the normal rules of stellar life and death are being rewritten within these chaotic gravitational confines. Lithium presents one of the most head-scratching anomalies. In the vast majority of stars, lithium is a fragile element that is quickly destroyed in the hot nuclear furnaces of a star's core. As a star matures, its surface lithium abundance plummets. Yet, in several of these systems, astronomers have found certain stars, often the hotter, more massive ones, that possess lithium levels far higher than any standard model would predict. It's like finding a log that has been sitting in a roaring fireplace for hours, yet remains unburned and cool to the touch. This lithium paradox points to some exotic process that is either creating new lithium faster than it can be destroyed or somehow protecting the existing lithium from the searing temperatures of the stellar interior. One compelling theory is that the incredible gravitational stresses from frequent close encounters with other stars are churning the stellar interiors, dredging up deep, lithium-rich material from layers that are normally dormant and bringing it to the surface where we can detect it. Alternatively, the lithium could be a recent contaminant delivered by a stellar sibling in a violent transfer of material. The story of carbon is equally perplexing. In some stars within the system, the carbon-to-oxygen ratio is wildly skewed. You might find a star that is incredibly carbon-rich, its atmosphere so saturated with carbon that it could potentially form soot and graphite clouds in its upper layers. Right next to it, another star might show a severe carbon deficiency. This isn't just a slight variation, it's a fundamental difference in the very building blocks of the star. Such dramatic disparities shouldn't exist between stellar siblings. This suggests a history of mass transfer on a colossal scale. Imagine a binary pair within the larger system where one star evolved faster, swelling into a giant and literally pouring its carbon-enriched outer layers onto the surface of its companion star. The donor star would be left stripped and deficient, while the recipient would become artificially enriched, its surface composition now telling the story of its neighbor's death rather than its own birth. In the tight gravitational quarters of a Quattuordecuple system, this kind of stellar cannibalism isn't just possible, it might be a regular occurrence. Perhaps the most telling clues come from the heavy elements, the metals forged in the hearts of massive stars and scattered across space in supernova explosions. The patterns of these elements act as a cosmic clock and a historical record. Generally, younger stars contain a higher abundance of these heavy elements because they formed from gas that had been seeded by multiple generations of supernova. Yet in these systems, that logical timeline is completely jumbled. Some stars show the classic signature of extreme youth, rich with iron and other metals. Others have the pristine, metal-poor composition of ancient stars that formed early in the universe's history. Finding these two extremes gravitationally bound together is like finding a medieval knight in full armor standing next to a modern-day soldier. Their very existence speaks to eras billions of years apart. This provides the strongest evidence yet that these systems are not families but fortresses, built by capturing stars from vastly different populations and generations across cosmic time, imprisoning a living history of the galaxy's chemical evolution within one gravitational net. Just when we thought the dynamics of these 14 star systems couldn't get any more complex, astronomers uncovered a detail so bizarre it seemed to defy the very logic of cosmic formation, the existence of counter-rotating subsystems. Picture the entire system as a colossal, chaotic disk of stars, all swirling around a common center of gravity. You'd expect some level of organized chaos, with most stars following the general direction of the spin, like water circling a drain. But the data revealed something entirely different. Within the larger whirl, there are distinct, tightly bound groups of stars, mini-families of 3 or 4 suns, that are moving in the complete opposite direction, like salmon swimming upstream against a powerful current. This isn't a minor discrepancy, it's a fundamental violation of how we understand star systems to be born. The standard model of star formation from a single, collapsing cloud of gas and dust predicts conservation of angular momentum. As the cloud contracts, it spins faster, and everything that forms from it, every star, every planet, should inherit that spin and continue rotating in the same direction. It's a cosmic legacy passed down from parent to child. Finding stars that blatantly ignore this inheritance is like discovering a family where half the children have entirely different DNA. It points to an origin story not of a single birth, but of a violent and dramatic assembly. The most compelling explanation for this celestial rebellion is a history of capture. These counter-rotating groups are likely the survivors of a cosmic collision, the remnants of an entirely separate star system that ventured too close to the gravitational fortress of the Quattuordecuple system eons ago. Imagine 2 distinct star clusters, each with its own unique spin direction, on a slow-motion collision course through space. When they finally meet, it's not a destructive crash of stars, but a gradual, gravitational tidal interaction. The smaller, invading system is shredded by the overwhelming gravity of the larger one. Most of its stars are scattered into the void, lost to interstellar space. But a lucky few, a tight-knit group that was already gravitationally bound to each other, are captured. They don't assimilate, they retain their original orbital identity, including their unique direction of spin, becoming a permanent but rebellious province within the larger stellar empire. This creates an environment of incredible gravitational tension. The interface between a prograde group and a retrograde group is a zone of fierce, shearing forces. When stars from these opposing factions make their inevitable close passes, the interaction is far more dramatic than a simple gravitational tug. It's a head-on confrontation of angular momentum, a cosmic traffic jam of epic proportions that generates intense shockwaves through the surrounding gas and plasma. These chaotic regions become hotspots for triggering new waves of star formation and for stripping the outer atmospheres from stars, leaving behind exposed, ultra-hot cores. The very presence of these counter-rotating factions is a ticking clock, a source of internal stress that constantly challenges the system's long-term stability, ensuring that the gravitational drama within this family of 14 never, ever ceases. And just when we thought we'd catalogued every possible anomaly, our telescopes revealed something that shouldn't exist at all. Vast, intricate disks of dust and gas encircling the entire system, glowing faintly in the infrared. Finding a protoplanetary disk around a single young star is common, but discovering one wrapped around a chaotic gravitational vortex of 14 stars is like finding a perfectly symmetrical snowflake surviving in a blast furnace. These aren't the smooth, placid rings we see around stars like Fomalhaut. These disks are warped, twisted, and full of bizarre features, spiral arms that look like cosmic whirlpools, strange gaps and voids, and stark, lopsided asymmetries that make them look nothing like the neat, flat disks we're used to. The existence of these disks alone is a minor miracle. The gravitational forces at play in the system's core should have long ago torn any primordial cloud of planet-forming material to shreds, scattering it into the void. The fact that a disk persists means it is constantly being replenished, likely from a truly apocalyptic source, the ongoing collisions between smaller bodies within the system itself. The frequent close passes between stars don't just alter orbits, they violently shake the vast cloud of comets, asteroids, and dwarf planets that must orbit the system's periphery. These gravitational jolts send countless icy bodies careening inward, where they inevitably smash into one another, grinding each other down into fine dust and gas that continually feeds and refreshes the disk. It's a self-sustaining cycle of destruction and renewal, a permanent dust storm generated by the system's own internal chaos. The most stunning features within these disks are the pronounced spiral arms. In a normal protoplanetary disk, such structures are the telltale signature of newborn planets, their gravity carving and sculpting the material as they orbit. But here, the spirals are far more intense and chaotic. They are not being carved by a single planet. They are the direct gravitational imprint of the entire system's overwhelming pull. As the 14 stars whirl around their common center of mass, their combined gravity creates powerful density waves that propagate through the disk, much like the spiral waves that give galaxies their iconic shape. These waves squeeze the dust and gas, triggering clumping and potentially even kickstarting the formation of new planets in these chaotic tidal zones, a process we've never witnessed anywhere else in the universe. Then there are the gaps. In comma systems, a clean, dark gap in a disk is almost a sure sign of a planet orbiting there, having swept its path clear of debris. But the gaps in these disks are different. They are ragged, partial, and often misplaced, not aligning with any predictable orbital distance. This suggests they are not being cleared by a single, steady hand, but by the much more violent and sporadic gravitational resonances of the stars themselves. A gap might appear where the orbital period of the dust particles resonates with the orbital period of a specific stellar subgroup, a rhythmic tug that acts like a gravitational sieve, ejecting any material that ventures into that zone. Other voids could be the scars of recent stellar encounters, regions where a passing star's gravity literally vacuumed up all the dust in its path during a close flyby. The profound asymmetries complete this picture of a disk under siege. One side of the disk might be bright and extended, while the opposite side appears faint and compressed. This lopsidedness is a frozen record of recent violence, likely caused by a close pass from a runaway star or a massive stellar subgroup that plowed through the disk, dragging a huge wake of material with it and leaving the other side depleted. This isn't a stable environment for planet formation. It's a turbulent construction site where the blueprints are being rewritten by gravitational earthquakes every single day. Yet, against all odds, the intense pressure from these density waves might be accelerating the process of planet formation, forcing dust grains to clump together at a far faster rate than in quieter systems. It suggests that even in the most hostile environments, the universe persists in its drive to build new worlds, finding a way to create order from the relentless chaos. And if the chaotic orbits and counter-rotating factions were not enough to confound us, the stars themselves present what is perhaps the most profound temporal paradox of all. When astronomers began to calculate the ages of the individual stars within these Quattuordecuple systems using standard stellar evolution models, they expected to find a family of sibling stars born from the same cloud at roughly the same time, all sharing a common age within a few million years of each other. The results, however, were nothing short of inexplicable. The data revealed a system that is quite literally impossible, a gathering of stars whose estimated ages are separated not by millions but by billions of years. Within the same gravitational family, you can find a vibrant blue-white O-type star, a brilliant newborn likely less than 10 million years old, orbiting alongside a cold, ancient red dwarf that stellar models suggest has been burning quietly for 12 billion years, a star that formed when the universe itself was in its cosmic infancy. This isn't a minor discrepancy, it's a chasm in time so vast it challenges the very notion of what a star system is. A star that is 12 billion years old has lived through almost the entire history of the universe. It witnessed the era of reionization, the formation of the first galaxies, and the quiet middle age of the cosmos. Its companion, the O-star, is a cosmic toddler by comparison, a temporary flash in the pan that will burn out and die in a spectacular supernova long before the red dwarf has even consumed 1% of its total fuel supply. For these two to be gravitationally bound as siblings is an utter impossibility under the standard model of star formation. They cannot have been born together. Their coexistence suggests a history far more dynamic and violent than a simple birth from a single cloud. This age paradox provides the most compelling evidence yet for the stellar capture theory on a truly epic scale. It suggests that these quattuordecuple systems are not natal families but gravitational fortresses, and their primary function is to capture and retain stars from wildly different eras and populations. The ancient red dwarf might be a primordial relic, one of the very first stars to form in our galaxy, which has been wandering the interstellar darkness alone for eons. Billions of years later, a dense young star cluster forms elsewhere in the galaxy, and within it, a massive O-type star is born. Through some incredible series of gravitational encounters, perhaps a close pass with a molecular cloud or an interaction with another cluster, this young cluster or a piece of it ventures too close to the ancient star. The overwhelming gravity of the larger system captures the young star, pulling it in and binding it forever to a companion that is older than the Milky Way's spiral arms. This process turns the entire system into a living museum of galactic stellar evolution. By studying the chemical composition of these stars, astronomers can take a core sample through cosmic time. The ancient star possesses a primordial atmosphere, almost entirely hydrogen and helium, with only trace amounts of heavy elements because it formed before generations of supernova had enriched the cosmos with metals. The young O star, by contrast, is metal-rich, its spectrum filled with the fingerprints of elements like iron, silicon, and oxygen that were forged in the hearts of stars that lived and died long after its ancient companion was born. Holding these two stars in the same gravitational prison allows us to directly compare the building blocks of the early universe with those of the modern era, all within a single, observable system. This age discrepancy is no longer just a puzzle. It is a unique opportunity, a chance to study the entire history of star formation and galactic chemical enrichment without having to look across the vast distances of space, because that entire history is written in the stars of a single, impossible family. Even the stars themselves seem stressed by their chaotic living arrangements, unleashing their fury in outbursts of energy so extreme they defy all classification. While our own sun occasionally hiccups with a solar flare, the eruptions within a quattuordecuple system are of an entirely different magnitude. These are not mere flares. They are cataclysmic events, stellar tantrums that can briefly outshine the combined light of every other star in the system. The pattern of these outbursts is what truly baffles astronomers. In a typical flare star, you might see a rough periodicity, a cycle linked to the star's rotation or internal magnetic dynamo. Here, there is no pattern, only chaos. The system's light curve in the X-ray and radio bands looks like the readout from a frantic heart monitor, with spikes of activity occurring randomly, sometimes hours apart, sometimes decades apart, with no predictable rhythm whatsoever. This relentless activity is a direct product of the system's gravitational torture chamber. The immense tidal forces generated during close stellar passes don't just alter orbits, they violently knead the interiors of the stars themselves. Imagine taking a stress ball and relentlessly squeezing and twisting it in your hands. That's what these stars endure on a constant basis. This mechanical stressing supercharges the star's internal dynamos, twisting their magnetic field lines into impossibly complex and unstable knots. The energy stored in these contorted magnetic fields is staggering, and when they finally snap, reconnecting into a simpler, lower energy state, they release that pent-up fury in a single, devastating burst across the entire electromagnetic spectrum. It's the stellar equivalent of a seismic earthquake after centuries of tectonic strain, but happening over and over again. The resulting superflares are so powerful they can strip the atmosphere from any nearby planet in a single event and bathe the entire system in lethal radiation for weeks. But the true oddity isn't just the power, it's the sheer variety. One flare might be a brilliant, short-lived burst of gamma rays, suggesting a magnetic reconnection event deep within a star's corona. The next could be a prolonged, weeks-long eruption in the radio band, indicating a massive ejection of charged particles trapped in magnetic loops. This diversity points to multiple, simultaneous trigger mechanisms. A flare might be set off by a direct tidal squeeze during a close pass, or indirectly, when the magnetic field of one star is violently yanked and distorted by the gravitational wake of a rapidly passing neighbor. The stars are essentially setting each other off in a chain reaction of magnetic violence, a constant feedback loop of gravitational and electromagnetic energy. This environment is so hostile that it challenges the very definition of a star, suggesting that in the most extreme gravitational pressures, stellar magnetic activity can be enhanced to levels we once thought were only possible during rare, catastrophic events like stellar mergers. But the electromagnetic strangeness isn't confined to high-energy outbursts. It extends into the serene, silent realm of radio waves, where astronomers have detected signals so peculiar they defy comparison to any known cosmic object. While scanning the skies with powerful radio telescopes, researchers have pinpointed emissions originating from these Quattuordecuple systems that are utterly unique. The signals present a bizarre dual personality, a combination of two components that should not logically coexist. One part of the emission is a steady, periodic pulse, a rhythmic beat as reliable as a cosmic metronome, ticking away with a consistency that suggests a rapidly spinning, incredibly dense object like a pulsar. Yet superimposed on this steady rhythm are wild, unpredictable bursts of radio energy, intense flashes that erupt without warning and then vanish back into the background noise, behaving more like the mysterious fast radio bursts that come from distant galaxies. This strange hybrid signal is a total mystery because it doesn't match the fingerprint of any known emitter. A classic pulsar, the super-dense, spinning core of a dead star, produces a remarkably clean and steady periodic signal as its lighthouse-like beam sweeps past Earth. The random bursts, on the other hand, are the hallmark of cataclysmic, one-off events. To find both a steady pulse and random bursts coming from the same pinpoint location in one of these systems is like listening to an orchestra where a drummer keeps perfect time while a cannon is fired at random intervals in the middle of the performance. It suggests a single source that is both stable and violently unstable at the same time. A paradox that has astronomers questioning their fundamental understanding of how stellar magnetospheres operate. The leading hypothesis to explain this radio riddle involves a scenario of unprecedented magnetic interplay. Imagine not one, but two or more highly magnetized neutron stars orbiting each other incredibly closely within the larger system. Each of these stellar corpses possesses a magnetic field trillions of times stronger than Earth's, and as they whirl around one another, their immense magnetospheres don't just coexist, they physically overlap and violently interact. The periodic pulse could be the steady beat of one pulsar's spin, its signal miraculously surviving the chaotic environment. The random bursts, however, could be the result of a sudden and catastrophic magnetic reconnection event occurring where the two magnetospheres grind against each other. As the stars move along their orbits, their magnetic field lines become twisted and stretched until the tension becomes too great, and they snap, reconfigure, and release a colossal amount of energy in a fraction of a second, appearing to us as a powerful radio burst. This would make the entire binary or trinary neutron star group a unified engine, generating both a predictable signal from its rotation and unpredictable explosions from the friction between its constituent parts. An even more exotic possibility is that we are witnessing the birth of an entirely new class of object, one that is only possible in the unique pressure cooker of a 14-star system. The immense gravitational forces could be crushing matter into states we cannot replicate or even model accurately. perhaps creating a singular neutron star with a complex, multi-pole magnetic field that is constantly being agitated by the gravitational tides of its many stellar neighbors. This external stressing could force the star to release its pent-up energy in these two distinct ways: a steady spin and sudden tectonic shifts in its magnetosphere. Whatever the cause, these strange radio emissions are more than just a curiosity. They are a direct transmission from one of the most extreme gravitational environments in the universe, offering us a chance to listen in on the complex and hidden magnetic conversations happening between stars trapped in an impossible dance. But the distortions go far beyond simple illusions of position. The collective gravity of 14 stars acts as a complex and dynamic lens, warping the very fabric of space to create a celestial hall of mirrors. This phenomenon, known as gravitational lensing, is typically associated with massive galaxy clusters bending the light from incredibly distant quasars. Yet here it occurs on a smaller, more intricate scale within the system itself. The sheer combined mass of the stars, particularly when they briefly align along our line of sight, is enough to create a noticeable lensing effect. The light from a star in the background of the system doesn't travel in a straight line to our telescopes. It is curved and bent as it passes through the gravitational well of the foreground stars. This results in multiple, distorted images of the same star appearing in different parts of the system. You might see 2 or 3 faint, ghostly copies of a single red giant, each a mirage created by the gravity of different stellar subgroups bending its light along separate paths. These phantom images shift and change in brightness as the stars move, a flickering funhouse effect that makes mapping the system's true geometry a monumental challenge. Astronomers must carefully disentangle which points of light are real stars and which are gravitational echoes, a process that requires comparing countless observations to track the motion of these illusions against the predictable orbits of the actual bodies. The lensing also acts as a natural magnifying glass. During these precise alignments, the light from a background star can be temporarily amplified, its brightness surging as the gravitational focus sharpens. This microlensing effect provides a fleeting but invaluable opportunity to study stars that would otherwise be too faint to observe in detail, offering a free upgrade to our telescopic power courtesy of the system's own immense gravity. It also inadvertently reveals the presence of otherwise invisible objects. A sudden, unexplained magnification event can signal the passage of a dark, massive body like a rogue planet or a stellar remnant, its presence betrayed only by its gravitational effect on the light of another. Beyond lensing, the orbital motion itself creates a constant relativistic light show. As stars whip around their chaotic paths at significant fractions of the speed of light, 2 key effects come into play: Doppler boosting and relativistic aberration. Doppler boosting causes a star to appear brighter when it is moving directly towards us and dimmer when moving away, as the light waves are compressed or stretched. In a normal binary system, this creates a gentle, predictable pulsation. But with 14 stars all moving in different directions at different speeds, the result is a chaotic, unpredictable strobing across the entire system, with stars randomly flaring and fading based on their instantaneous velocity relative to Earth. Relativistic aberration, often called the headlight effect, further distorts our view. A star moving at extreme velocity will appear to have its light concentrated in the direction of its motion. From our perspective, a star hurtling sideways across our line of sight might suddenly seem to focus its light, becoming momentarily brighter and more focused than its stationary properties would allow. This combines with the Doppler effect to create a complex, ever-changing map of apparent brightness that has little to do with the star's actual sizes or temperatures and everything to do with their frenzied orbital dance. To understand the true nature of these stars, astronomers must first become masters of decoding this high-speed relativistic distortion, subtracting the effects of their motion to reveal the reality beneath the illusion. For all the chaos and complexity we've explored, there remains one overarching, humbling mystery that towers above the rest: the fact that these systems exist at all. The presence of a functioning Quattuordecuple system doesn't just push the boundaries of our current models. It crashes straight through them, confronting us with a reality that our most sophisticated theories of gravitational dynamics insist should be impossible. Every principle we have about multi-body orbital stability suggests that a system of this size and complexity should have torn itself apart within a few million years, a mere blink in cosmic time. Their enduring existence, therefore, is not just an oddity. It is a direct and profound challenge to our fundamental understanding of how gravity operates on the grandest scales. The core of the problem lies in a concept known as the n-body problem. For two masses like the Earth and the Sun, calculating their mutual orbits is elegantly simple, governed by equations with clear, stable solutions. Introduce a third body, however, and the mathematical elegance shatters. The system becomes chaotic, its long-term future inherently unpredictable because tiny, imperceptible changes in the initial positions or velocities of the bodies amplify over time, leading to wildly different outcomes. This is why we can predict solar eclipses centuries in advance with pinpoint accuracy, but cannot predict the exact orbital configuration of Jupiter's moons a billion years from now. Now multiply that inherent chaos not by 3 but by 14. The level of complexity doesn't just increase, it explodes exponentially, creating a feedback loop of gravitational perturbations so intense that our most powerful supercomputers cannot accurately simulate the system's evolution beyond a short window of time without the predictions devolving into nonsensical noise. This chaos should be self-correcting. The most statistically probable outcome for any overly complex gravitational system is a dramatic simplification. Stars should be flung clear of the group, achieving escape velocity to become lonely runaways in the interstellar void. Alternatively, the countless close encounters should frequently result in direct collisions, merging stars into new, larger bodies and reducing the overall number. The fact that we observe numerous systems that have clearly avoided both of these fates for hundreds of millions of years points to a stunning possibility: that there are hidden stability mechanisms at work, gravitational sweet spots or resonant patterns that we have not yet discovered or mathematically defined. One tantalizing idea is that these systems achieve a state of meta-stability through a hierarchy of subsystems. It's not 14 individual stars all pulling on each other at once in a free-for-all. Instead, they appear to organize themselves into a series of nested, stable pairs and trios. You might have a tight central binary acting as a gravitational anchor. Around that, a wider orbit triple system rotates as a single unit. Further out, two more binary pairs orbit the central core. Each of these smaller groups is internally stable, and they interact with each other at distances great enough that their gravitational perturbations are minimized, creating a layered, Russian doll structure of stability within the overarching chaos. This hierarchical organization could be the key, providing a framework that channels the system's chaotic energy into a persistent, long-lived pattern. Another, more speculative theory involves the concept of chaotic stability. It suggests that for a brief period in cosmic time, the very chaos of the system becomes its own saving grace. The orbits are so wildly intertwined and the interactions so frequent that the system exists in a constant state of gravitational adjustment. It never settles into a predictable pattern long enough for a single, catastrophic instability to develop and eject a member. Instead, the constant near misses and gravitational slingshots create a dynamic equilibrium, a perpetual motion machine of stars where the energy is constantly being redistributed in a way that, against all odds, prevents any one star from gathering enough energy to break free. It's a precarious, high-wire act, but one that the system manages to maintain through its own relentless turbulence. This forces a monumental shift in astrophysics. We can no longer view these Quattuordecuple systems as failed clusters or mathematical impossibilities. We must instead see them as the ultimate natural laboratories for testing the limits of gravitational theory. Their existence is a concrete data point proving that our current n-body simulations, while excellent for simpler systems, are missing a crucial piece of the puzzle. That missing piece could be the subtle influence of dark matter halos subtly bolstering the system's gravity, the moderating effect of widespread protoplanetary disks acting as a gravitational buffer, or an entirely new aspect of orbital resonances that only emerges with such a high number of participants. Each stable Quattuordecuple system is therefore a message from the universe, a clue written in the language of gravity, telling us that there is still profound and beautiful physics left for us to discover. This taxonomic crisis led to the creation of entirely new classes of variable stars, categories born purely from the necessity to describe the pandemonium of a Quattuordecuple system. Astronomers found they couldn't simply slap an existing label like Algol type or Cepheid onto these objects. The light curves were too complex, too chaotic, representing a superposition of dozens of different phenomena all happening at once. The official variable star designation, typically a simple combination of letters and numbers denoting its order of discovery in a constellation, became almost a formality, a meaningless catalog entry that utterly failed to capture the object's true nature. To truly classify them, researchers had to invent new, multi-layered descriptors that read less like astronomical classifications and more like complex medical diagnoses. The resulting hybrid classification might look something like Eb/Sep/Flare/Eruptive, MP, which translates to a star that is simultaneously an eclipsing binary, a Cepheid pulsating variable, a flare star, and an eruptive variable, with the final MP indicating the multiple phenomena that defy easy separation. This isn't just an academic exercise, it's a fundamental shift in how we think about stellar behavior. In a typical variable star, the change in brightness tells a single, clean story, a pulsation, an eclipse, an eruption. Here, the light curve is a palimpsest, a document written and rewritten by multiple authors, where the signature of one event is superimposed upon and often distorted by the signature of another. A regular pulsation rhythm might be periodically interrupted by a deep eclipse from a different star, which is then overlain by a sudden flare from a third, all of which slightly alters the amplitude of the next pulsation. Untangling this requires sophisticated computer algorithms designed to isolate individual signals, a process akin to trying to separate the individual instruments in a symphony recording using only a single microphone. This classification nightmare actually provides an unprecedented opportunity to study stellar physics in a hyper-connected environment. By painstakingly deconstructing these complex light curves, astronomers can observe how different stellar processes influence one another. They can study how a strong flare on one star might temporarily suppress flaring activity on a nearby magnetically linked companion, or how the intense tidal gravity during a close stellar pass can actually dampen the pulsation amplitude of a Cepheid variable for decades. Each system becomes a natural laboratory for testing how stellar phenomena interact, offering insights we could never gain from studying isolated stars. The very complexity that made them so difficult to classify is now their greatest gift, revealing the hidden conversations and feedback loops that govern stellar lives when they are lived in such incredibly close quarters. Even their collective journey across the galaxy holds a strange and telling signature. When astronomers track the motion of a typical star cluster, the individual members drift through space together in a relatively coherent and predictable way, like a school of fish moving as one. But when they plotted the precise proper motion, the tiny, year-to-year shift in position against the backdrop of more distant stars of the members within a Quattuordecuple system, the data revealed a pattern of organized chaos that was entirely unexpected. The system moves as a single, massive unit, as its immense collective gravity dictates it must, but the individual stars within it do not follow neat parallel paths. Instead, they trace a complex braided trajectory, each star weaving and bobbing around the group's common center of mass as the entire system hurtles through the galaxy. This peculiar dance is a direct reflection of the internal gravitational turmoil. The stars are not simply orbiting a central point. They are constantly being slingshotted and perturbed by their close encounters, causing their positions relative to the group's center to change dramatically over time. From our distant vantage point, this creates the illusion of a system that is both tightly bound and yet internally seething with independent motion. The overall path across the sky is smooth and linear, but superimposed upon it is this frantic, shimmering vibration of 14 stars, each trying to pull in a slightly different direction, only to be relentlessly corralled back by the overwhelming gravity of the whole. It's the proper motion equivalent of watching a swarm of bees moving together as a cloud, with each individual bee buzzing in its own frantic, unpredictable loop within the group. This bizarre pattern provides a crucial clue to the system's origin and mass. The fact that the entire group moves with a single, coherent proper motion proves that it is a truly bound system, not a chance alignment of unrelated stars drifting past each other. However, the amplitude of the internal stellar wobbles, how far each star deviates from the group's average path, allows astronomers to perform a delicate gravitational census. By measuring these deviations, they can estimate the total mass of the system required to keep such wildly oscillating members from flying off into space. The results consistently point to a startling conclusion. There is significantly more mass holding these systems together than can be accounted for by the visible stars alone. This missing mass presents a profound mystery. One possibility is that the system is filled with a vast number of failed stars, brown dwarfs, that are too dim to see, or a swarm of Jupiter-sized planets that were stripped from their parent stars during close encounters and now wander the system freely, contributing gravity but no light. An even more exotic explanation involves dark matter. While dark matter is thought to be diffusely distributed on a galactic scale, some theories suggest it could become gravitationally attracted to and concentrated around extremely massive, dense objects. A Quattuordecuple system, with its immense gravitational pull, could act as a cosmic magnet, gathering a localized halo of dark matter around itself. This invisible, massive halo would then provide the extra gravitational glue needed to explain the system's cohesive proper motion and its ability to retain runaway members that should have escaped. If true, this would be the first evidence of dark matter not just permeating the galaxy, but being actively bound to and shaping the dynamics of a single, specific star system, offering a completely new way to study this elusive substance. Nestled deep within the swirling chaos of 14 stars, astronomers have uncovered pockets of such incredible intimacy that they defy all expectations. It seems that within the grand, sprawling dance of the entire system, the most dramatic relationships are not between the 14 members, but between two stars that have chosen to orbit each other in an impossibly tight embrace. These are not just binary pairs, these are stellar couples locked in a frantic, close-distance waltz with orbital periods measured not in years but in mere days. Imagine two stars of immense size, each potentially larger than our own Sun, circling one another so rapidly that a full year on a planet orbiting them would pass in less than a week. Their surfaces are not separated by millions of miles. In some cases, they are so close that their outer atmospheres literally touch, creating a shared, superheated envelope of plasma that forever binds them together in a violent, passionate dance. The existence of these tight binaries within an already complex system adds a staggering new layer of gravitational engineering. It creates a system within a system, a hierarchical masterpiece of orbital mechanics. Picture this: two stars nearly touching whirl around their common center of gravity in a blindingly fast orbit. This entire furious pair then, as a single combined unit, orbits a third star over a period of several years. That triplet then, as a group, orbits another distant pair, and so on, building up like cosmic nesting dolls until all 14 stars are bound. This hierarchy is the secret to the system's improbable stability. The incredible gravitational energy that would normally tear 14 individual stars apart is instead neatly packaged and contained within these smaller, stable subgroups. The tight binary acts as a fundamental anchor, a solid gravitational brick in the foundation of the entire chaotic structure. The environment within these close binaries is one of breathtaking extremes. The gravitational forces are so powerful that they distort the stars themselves, pulling them out of their normal spherical shapes into elongated egg-like forms, constantly stretching towards each other. This tidal distortion generates immense internal friction, heating the stars' interiors to even more incredible temperatures and supercharging their magnetic dynamos. The space between them is a perpetual inferno, dominated by the colossal collision of their stellar winds. Each star blows a hurricane of charged particles into space, and these two hurricanes smash into each other at a significant fraction of the speed of light, creating a permanent shock front that glows with intense X-rays and effectively cooks anything in the immediate vicinity with unimaginable levels of radiation. This leads to some of the most exotic and poorly understood stellar phenomena we have ever witnessed. The most spectacular is mass transfer. In many of these pairs, one star has begun to expand as it ages. In a normal binary, this might lead to a simple transfer of material. But here, with the stars so incredibly close, the process becomes a raging torrent. The outer layers of the expanding star are violently stripped away by the gravitational pull of its companion, forming a vast, swirling disk of superheated gas that spirals down onto the other star's surface. This isn't a gentle flow, it's a cataclysmic accretion process that can trigger periodic thermonuclear explosions on the receiving star's surface, creating regular outbursts that make the entire binary temporarily brighten by a factor of 100. In some cases, the transfer is so efficient that one star is completely consumed, leaving behind a stripped-down, ultra-dense core, while its partner becomes artificially rejuvenated, bloated and bright from its stolen atmosphere. This process effectively resets the evolutionary clock for both stars, creating a bizarre pair where a dead stellar remnant orbits a seemingly youthful, massive star, a relationship that could never have formed naturally through simple stellar birth. Yet another layer of this gravitational mystery comes from the simple, undeniable math of orbital motion. By applying the same fundamental laws Kepler and Newton gave us centuries ago, astronomers can calculate the precise mass required to keep a star moving on its observed path. For a star in a wide, lazy orbit, the required central mass is modest, but for those runaway members on incredibly long, stretched-out paths, or for inner stars whipping around at blistering speeds, the numbers tell a startling story. The calculated mass needed to produce those observed velocities is consistently and significantly larger than the combined mass of all 14 visible stars put together. There is simply more gravity present than the things we can see can possibly account for. This discrepancy points to a vast amount of mass that is completely invisible to our telescopes, hidden in plain sight, its presence felt only through its unmistakable gravitational pull. This missing mass could take several forms, each more fascinating than the last. One strong candidate is a population of brown dwarfs, often called failed stars. These are objects that formed with too little mass to ignite sustained hydrogen fusion in their cores. They are massive enough to exert a strong gravitational pull, but too small and cool to shine brightly with visible light, lingering instead as faint infrared emitters that are incredibly difficult to spot against the brilliant glare of 14 active stars. Dozens or even hundreds of these dark orbs could be swarming through the system, their collective gravity providing a massive, unseen scaffold that helps bind the entire structure together. Alternatively, the missing mass could be in the form of a staggering number of rogue planets, worlds that were gravitationally unmoored from their parent stars during close encounters and now wander the system freely. A vast Neptune-sized planet here, a super-Earth. There are thousands of such objects, each contributing a tiny bit of gravity, could add up to a significant fraction of a solar mass, all while remaining virtually undetectable with current technology. The most dramatic possibility, however, is that the system's ultimate gravitational anchor is a single, monstrously dense object, a stellar mass black hole. Imagine a black hole with the mass of 5 or 10 suns, sitting at the system's gravitational center of mass. Its immense pull would act as a master conductor for the chaotic stellar dance, providing a stable focal point that the 14 visible stars all orbit around. This would elegantly explain the system's ability to retain its runaway members. Even a star flung outward at high velocity would still be held in check by the deep, inescapable gravity well of the central black hole. It would also provide a source of immense energy, potentially explaining the intense and variable X-ray emissions detected from these systems, which could be generated by gas torn from the atmospheres of closely passing stars as it spirals into the black hole's accretion disk. The presence of such an object would transform our understanding of the system from a collection of stars into something far more immense, a miniature galaxy with a central black hole governing the motion of its stellar constituents. This hidden mass, in whatever form it takes, is the silent partner in the dance, the unseen hand that may be the ultimate reason these 14 star families can survive against all odds. What's truly bizarre is that this gravitational maelstrom doesn't just alter the paths of these stars, it fundamentally changes how they spin on their own axes. Imagine a figure skater pulling their arms in to spin faster. That same principle of angular momentum governs stellar rotation, but within a Quattuordecuple system, the rules are thrown out the window. We find stars spinning at velocities so extreme they should, by all rights, tear themselves apart, flinging their own atmospheres into space. Yet right beside them, we observe other stars rotating with a lethargy that defies explanation, spinning so slowly that their surface activity is almost dormant. This bizarre dichotomy of rotation rates is a direct and stunning consequence of the system's endless gravitational tug-of-war, a clear signature of the complex energy transfers happening between these 14 stellar partners. The rapid spinners present a spectacle of sheer stellar violence. These are often the stars that have endured a recent, incredibly close gravitational encounter. As two stars swing perilously near each other, the tidal forces between them are immense. It's less like a gentle tug and more like one star reaching out and giving the other a powerful slingshot-style shove. This gravitational interaction can transfer a massive amount of angular momentum, dumping rotational energy into one star like a crank on a jack-in-the-box, winding it tighter and tighter. The result is a star that begins to whirl on its axis at a dizzying pace, completing a full rotation not in weeks or months like our Sun, but in a matter of hours. Its equator bulges outward from the centrifugal force, and its magnetic field, wound up by the frantic spin, becomes a tangled mess of energy, leading to a constant barrage of superflares and violent surface activity. These stars are the system's agitated giants, their rapid rotation a visible scar from a recent gravitational assault. On the opposite end of the spectrum are the inexplicably slow rotators. These stars are the true enigmas, and their languid spin is perhaps an even greater puzzle than the frenzied ones. Standard stellar models predict that stars should maintain a certain baseline rotation rate based on their mass and age, gradually slowing down over billions of years. But these stars are spinning down at a rate that is orders of magnitude faster than any internal process could explain. It appears that the same complex interactions that speed some stars up are actively applying a brake to others. One compelling theory suggests that a star's own stellar wind, the stream of charged particles flowing from its surface, can be dramatically amplified and manipulated by the powerful magnetic fields of its close neighbors. If a star is orbiting in a region where the ambient magnetic field is opposed to its own, the resulting interaction could act like a magnetic drag, effectively applying a constant, system-wide brake that saps its rotational energy over time, leaving it spinning in slow motion against the backdrop of celestial chaos. This creates a system-wide economy of spin, a constant transfer of rotational energy from one star to another through their gravitational and magnetic links. A close pass between two stars isn't a simple event, it's a transaction. One star might leave the encounter spinning faster, having stolen angular momentum from the other, which itself is now rotating more slowly. This makes the rotational speed of any single star a temporary state, a snapshot in an endless dance of acceleration and braking. A star that is a rapid spinner today might be slowed to a crawl a million years from now after a different gravitational interaction, only to be wound up again later. This dynamic environment means that a star's current rotation rate tells us less about its innate properties and more about its recent gravitational history, acting as a living logbook of its most recent close encounters within the system's chaotic web. Perhaps the most humbling paradox of these systems is their sheer endurance, a longevity that stands in direct defiance of our most advanced computer predictions. Every model of gravitational interaction tells us that a gathering of 14 massive bodies should be a temporary arrangement, a flash in the pan destined to dissolve into chaos within a few million years. The gravitational perturbations, the close encounters, the sheer energy coursing through the system, it all points toward a rapid and violent dissolution. Stars should be flung into the void, others should collide in brilliant mergers, and the entire delicate structure should simplify itself into something far less complex. And yet, the observational evidence tells a completely different story. The chemical composition of the stars, particularly the presence of those ancient metal-poor members, suggests these systems are not young. They are cosmic elders, having persisted for billions of years, surviving through epochs of galactic history that saw the rise and fall of countless simpler star clusters. This creates a baffling contradiction between theory and observation. Our simulations, which work flawlessly for predicting the orbits of planets or the dynamics of binary stars, break down when faced with this level of complexity. The problem is one of exponential error. In an n-body simulation, the computer calculates the gravitational pull each star exerts on all the others for each tiny increment of time. But the equations of motion for such a system are famously chaotic, meaning the tiniest rounding error in the 15th decimal place of a single calculation will, over millions of simulated years, snowball into a completely unrealistic outcome. The simulation might show a star being ejected when in reality it would have stayed bound, or it might predict a collision that would never actually occur. The system's real-world stability suggests there are hidden damping factors or resonant balances that our current models simply cannot capture, subtle gravitational harmonies that emerge from the apparent chaos to gently shepherd the stars and prevent catastrophic disintegration. One compelling explanation for this ancient stability is the concept of hierarchical organization. It appears the system isn't a free-for-all of 14 stars all pulling on each other equally. Instead, it's likely structured like a series of nested gravitational partnerships. Imagine a tight central binary pair locked in a stable embrace. Orbiting them at a wider distance is a triple system, itself internally stable. Further out, two more binary pairs circle the core. Each of these smaller subgroups is relatively stable on its own, and their interactions with each other occur over longer timescales and greater distances, minimizing the disruptive potential. This layered structure channels the system's immense gravitational energy into a persistent, long-lived pattern, turning a potential riot into a complex but organized dance. The system isn't avoiding chaos, it's managing it, using its own internal hierarchy to distribute energy in a way that prevents any single star from gathering enough momentum to break free. This incredible longevity forces a monumental shift in our perspective. We can no longer view these Quattuordecuple systems as failed clusters or mathematical flukes. We must instead see them as the ultimate cosmic survivors, resilient gravitational entities that have somehow mastered the physics of coexistence on a grand scale. Their continued existence against all odds suggests that stability in the universe may not always mean simplicity and quiet order. It can also be found in a state of persistent, managed turbulence, a complex equilibrium where chaos and order are not opposites but partners, working in tandem to create structures of breathtaking durability and beauty. The space between these 14 stars is anything but empty. It's a seething, dynamic battlefield where the fundamental forces of nature collide in a spectacular and unpredictable display. Imagine the stellar wind from a single star not as a gentle breeze, but as a supersonic hurricane of charged particles, a relentless outflow that carves out a vast bubble in the interstellar medium. Now picture 14 of these hurricanes all blowing at once, from stars of different sizes, temperatures, and ages, their gusts slamming into one another from every conceivable direction. The result is a labyrinth of colliding shock fronts, a constantly shifting maze of unimaginably hot plasma and tangled magnetic field lines where the very notion of a calm, predictable environment is completely erased. This chaotic interplay creates what can only be described as migrating habitable zones, regions where conditions might be right for liquid water to exist on a planet's surface, but these zones are nothing like the stable, donut-shaped rings we imagine around single stars. In a Quattuordecuple system, the habitable zone is a shimmering, ghostly thing, a complex, multidimensional volume of space that contorts, stretches, and splits apart as the stars whirl through their chaotic orbits. A planet might find itself nestled perfectly within this comfortable region for a few centuries, enjoying a temperate climate under the light of 3 gentle suns. But then, a massive O-type star on its long, elliptical journey swings into the inner system, and its intense ultraviolet radiation floods the space around it. In a matter of decades, that once hospitable zone is violently pushed outward, shrunk, or completely obliterated, leaving any world within it scorched and sterilized. The climate on such a planet wouldn't just change with the seasons. It would undergo geological scale upheavals on a timescale short enough to be observed by its inhabitants, a relentless cycle of paradise and apocalypse dictated by the orbital ballet of its 14 suns. Adding to this complexity is the incredible pressure of light itself. Radiation pressure, the faint but constant push exerted by photons streaming from a star, becomes a powerful shaping force in this crowded arena. For dust grains and tiny asteroids, this pressure is a dominant factor, preventing them from accreting into larger bodies in some regions while herding them into dense clouds in others. The combined light of 14 stars creates zones of extreme radiation pressure that can literally blow the atmospheres off of planets that wander too close to the system's brilliant core, while in the colder outer reaches, the weakness of this pressure allows for the slow, quiet accumulation of material. This means the very process of planet formation is subject to wild regional variations, with some areas of the system effectively sterilized of building blocks while others become factories for creating strange, new types of worlds. Perhaps the most bizarre environments are those shaped by the clashing of immense magnetic fields. Each star is a powerful magnet, and as they orbit and tumble, their magnetic fields don't just overlap, they violently reconnect. Where the field lines from 2 stars cross and snap, they create vast natural particle accelerators in the void, regions where electrons and protons are whipped up to nearly the speed of light. These particles then spiral along the magnetic field lines, emitting intense synchrotron radiation, painting the system with brilliant but invisible glows in the radio spectrum. For any hypothetical world, this would mean the space around it is constantly crackling with high-energy particles, a permanent radiation storm that would make the surface a challenging place for life as we know it to gain a foothold, yet might provide the energy for truly exotic biochemistries deep beneath an icy crust or within protected subsurface oceans. The environment around these 14 stars is a testament to the universe's creativity, a cosmic experiment in extreme physics where the normal rules are suspended and replaced with a new, more complex set of laws we are only beginning to decipher. And just when we think we've catalogued the chaos of the individual systems themselves, a far grander pattern emerges when we zoom out to a galactic scale. Mapping the precise locations of every known and suspected Quattuordecuple system reveals something astonishing. They are not scattered randomly across the Milky Way like handfuls of sand. Instead, they appear to be clustered, congregating in very specific and telling regions of our galaxy. A disproportionate number of these gravitational giants are found within the tumultuous environment of the galactic bulge, that dense, star-packed region surrounding the supermassive black hole at our galaxy's heart. Significant groupings also appear along the inner edges of certain spiral arms, particularly in areas associated with the galaxy's most intense and recent star-forming activity. This is no cosmic coincidence. This distribution is a massive clue scrawled across the heavens, pointing directly to the unique conditions required to forge and sustain these 14 star marvels. The strong preference for the galactic center makes perfect, terrifying sense when you consider the sheer density of that environment. The central bulge is a stellar metropolis, a place where stars are packed so tightly that gravitational encounters are not rare events, they are a constant, everyday reality. In the suburbs of the galaxy where our sun resides, stars are distant neighbors, passing each other once every few million years. In the bulge, it's a perpetual cosmic traffic jam. This dramatically increases the probability of the capture events that likely built these systems. A young, massive multiple star system forming there wouldn't have to drift far or wait long before having a close encounter with another system, allowing it to act as a gravitational seed, snowballing in size by pulling in and binding other stellar groups through a series of mergers and acquisitions. The relentless gravitational tides from the central supermassive black hole itself may also play a role, somehow helping to stabilize these complex systems once they form, or even catalyzing their creation by forcing smaller systems into close proximity. The clustering along specific spiral arms tells a different but equally important story. Spiral arms are not fixed structures made of stars, they are density waves like traffic jams moving through the galaxy. As a cloud of gas and dust enters this wave, it gets compressed, triggering furious bursts of new star formation. The most massive and dense molecular clouds, the ones capable of fragmenting into the numerous cores needed to form a large multiple system, are most commonly found in these active regions. Therefore, it's logical that the spiral arms would be the primary birthplaces for these systems. But the story doesn't end there. The fact that we find mature Quattuordecuple systems still located within or very near these arms rather than having drifted far away is critically important. It suggests that the immense gravitational binding energy of a 14-star system makes it incredibly resistant to the shearing forces that typically tear star clusters apart as they orbit the galaxy. These systems are so massive and tightly knit that they can survive the journey through the galaxy's gravitational field for billions of years, acting as enduring landmarks that trace out the very regions where the most extreme star formation in the Milky Way's history has occurred. Their unusual distribution is a frozen record of the galaxy's most fertile and violent stellar nurseries. But beyond the grand chaos of orbits and collisions lies a far more subtle mystery, one that reveals itself not in violent eruptions, but in the quiet, meticulous measurement of time itself. Astronomers monitoring these systems have detected something extraordinarily faint yet profoundly significant: tiny, inexplicable hiccups in their celestial clocks. After meticulously tracking the orbits for years, they can predict when one star should eclipse another down to the precise second. Yet sometimes the eclipse arrives a fraction of a second early. Other times it's a fraction of a second late. These are not errors in measurement, they are consistent, real deviations, minute but detectable variations in the orbital timing that reveal the system's invisible gravitational hands at work. These timing variations are the system's way of whispering its deepest secrets. According to Kepler's laws, a star in a stable orbit should complete each loop in exactly the same amount of time, like a perfect metronome. The fact that the rhythms are off means something is subtly tugging on the stars, gently speeding them up or slowing them down in ways that our current maps of the system's mass cannot account for. It's the gravitational equivalent of feeling a ghost tap on your shoulder in a room you thought was empty. The most straightforward explanation is the presence of additional, unseen mass within the system, bodies too dark or too small for our telescopes to spot directly. This could be a swarm of Jupiter-sized planets weaving between the stars, their cumulative gravity imparting tiny nudges, or perhaps a few brown dwarfs, those failed stars that are massive enough to exert a pull but too dim to see against the glare of their brilliant siblings. However, some of these timing anomalies are so strange that they defy even these exotic explanations. In a handful of systems, the pattern of acceleration and deceleration doesn't align with the periodic tug of an orbiting body. Instead, it appears as a single, one-time jump in the timing, as if the entire system received a gentle, unseen shove from a direction that doesn't correspond to any known object. This has led to more speculative, thrilling possibilities. Could we be detecting the gravitational wake of a rogue black hole passing through the system's outskirts? Or perhaps we are witnessing the faint cumulative effect of dark matter, not just as a diffuse halo, but clumped around the system in ways we never predicted. The most profound possibility of all is that these minute timing errors are a signature of physics beyond our current understanding of gravity. A hint that in these extreme environments, Einstein's theory of general relativity requires a slight but measurable adjustment. Each tiny fluctuation in the clockwork is a potential clue, a data point in a cosmic experiment that is testing the very laws of the universe on a scale we are only just beginning to perceive. And now we arrive at a mystery that connects the impossibly small to the unimaginably vast, linking the chaotic dance of 14 stars to one of the most profound enigmas in all of modern astronomy: fast radio bursts. Imagine a flash of energy so powerful it can outshine 500 million suns, a burst of radio waves that screams across the cosmos for billions of years, yet lasts for less time than it takes to blink. These fast radio bursts, or FRB, have bewildered scientists since their discovery, with theories ranging from colliding neutron stars to messages from advanced civilizations. But recent, highly controversial evidence suggests a surprising new source for at least some of these cosmic sirens: the turbulent hearts of Quattuordecuple star systems. The hypothesis is as stunning as it is simple: that the very conditions we've been exploring, the violently interacting magnetic fields, the colliding stellar winds, the gravitational slingshots, might be generating these previously inexplicable explosions of energy. The initial clue was a matter of celestial cartography, as astronomers painstakingly pinpointed the origins of more and more repeating FRBs, those that flash not just once, but over and over again from the same location. They began to map them onto the sky. A handful of these persistent sources were traced back to regions of space known to host extreme stellar environments. In at least 2 cases, the incredibly precise localization led right back to a known Quattuordecuple system. The probability of this being a random alignment is astronomically low, forcing the scientific community to consider a once unthinkable connection. It appears that within these 14 star families, the conditions might be just right to fabricate a phenomenon that, until now, we thought required the most exotic of single objects like magnetars or merging black holes. The proposed mechanism is a symphony of magnetic violence on a scale we can barely comprehend. Picture not just 2, but 3 or 4 highly magnetized neutron stars, the super-dense corpses of dead suns, all orbiting within the same chaotic gravitational web. Each of these objects possesses a magnetic field so powerful it could strip the information from a credit card from halfway across the solar system. As they whirl through their frenetic paths, the magnetospheres of these stars don't just pass by each other, they physically overlap, their field lines grinding together like cosmic tectonic plates. The stress and tension in these regions build to an unbearable level until, in a catastrophic instant, the magnetic field lines snap and reconfigure in a simpler state. This event, known as magnetic reconnection, releases a staggering amount of pent-up energy in a fraction of a millisecond, accelerating charged particles to nearly the speed of light. It is this sudden, explosive release that we detect billions of years later as a brilliant, fleeting flash of radio waves, a fast radio burst. What makes the Quattuordecuple system the perfect engine for this is the constant agitation. In a calmer environment, a magnetic reconnection event might be a rare occurrence, but here the gravitational chaos ensures it is a near-constant process. The neutron stars are perpetually being jostled by the gravitational pulls of their many massive neighbors, their orbits perturbed, their spins altered. This external forcing violently churns their magnetospheres, making them fundamentally unstable and priming them for these explosive releases. The system doesn't just create the conditions for one FRB, it creates a factory for them, a natural particle accelerator that can fire off bursts repeatedly, which perfectly explains the behavior of the repeating FRBs that have been linked to these locations. The incredible power of the burst could be drawn from the immense rotational energy of the neutron stars themselves, with the magnetic reconnection event acting as a cosmic trigger, tapping into that energy reservoir and converting it into a directed blast of radio waves. Of course, this theory is far from settled. The astronomical community remains deeply divided. Skeptics argue that the energy required for the most powerful FRBs is simply too great to be generated by anything less than a single super-energized magnetar or a cataclysmic merger. They posit that the link to the Quattuordecuple systems is coincidental, that the FRB is actually originating from something else within the same general region, perhaps a more conventional source hiding in the glare of the 14 stars. Proponents counter that our models for energy release in such complex magnetic environments are still in their infancy, and that the combined effect of multiple neutron stars acting in concert could indeed reach the required thresholds. They point to the unique hybrid radio signals already detected from these systems, the combination of a steady pulsar-like beat with random, bursty emissions, as a possible lower energy preview of the full FRB phenomenon, a smoking gun that suggests we are already hearing the system's magnetic turbulence at a lower volume. This controversy is exactly what makes the link so electrifying. It pushes the boundaries of what we believe is possible and forces us to consider that the universe might be using the most complex stellar laboratories imaginable to brew up its most mysterious signals. Predicting the ultimate fate of a Quattuordecuple system is less like forecasting weather and more like trying to predict the exact outcome of 100 simultaneous chess games being played on a single, shaking table. The sheer number of variables and the system's profound sensitivity to initial conditions make its long-term future inherently unknowable in detail. Yet, by applying the fundamental laws of physics and stellar evolution, we can map out the most probable, spectacular, and terrifying pathways these gravitational families might take, each one a potential apocalypse on a cosmic scale. The first and most likely catalyst for a system-wide catastrophe is the death of its most massive members. Remember, the largest stars burn through their fuel at a ferocious rate and live the shortest lives. In a system teeming with stellar behemoths, it's not a question of if a supernova will occur, but when, and more importantly, what chain reaction it will trigger. The death of a single supergiant would be a cataclysmic event under any circumstances, but within this delicate gravitational web, it is a precision strike against the very architecture of stability. A core collapse supernova is not a symmetric explosion, it is a violently asymmetric event. The dying star can experience a kick from neutrinos streaming out in one direction, ejecting it from its position at tremendous speed or altering its trajectory in a completely unpredictable way. If the star is part of a tight binary or a central gravitational anchor, its sudden death or violent repositioning is like snapping the main support cable on a suspension bridge. The entire local subsystem, which had achieved a precarious balance, would be thrown into instant and irreversible chaos. The surviving stars, now missing a key gravitational partner, would be sent careening onto new, wildly perturbed paths, inevitably leading to a series of close encounters that were previously avoided. This could initiate a domino effect of stellar collisions. Two stars, nudged onto intersecting paths by the supernova's aftermath, might not simply pass by each other, they could merge in a titanic eruption of light and energy. A stellar merger is one of the most energetic events in the universe short of a supernova itself. If the colliding stars are both large, the resulting amalgamation could create a single, monstrously massive star that itself is now primed for a rapid and dramatic death, potentially as a hypernova capable of producing a long-duration gamma-ray burst. This newly formed giant would then become a new source of instability, its immense gravity further perturbing the orbits of every other star in the system, potentially setting the stage for the next collision or supernova in a chain reaction of stellar violence. The most exotic possibility arising from this chaos is the formation of a Thorn-Zitkow object. This hypothetical stellar oddity is a Russian doll of a star, a red supergiant or hypergiant whose core has been replaced by an entire neutron star. Imagine a supernova explosion in a tight binary pair where the neutron star remnant, instead of being ejected, is kicked directly into the outer layers of its gigantic companion. The neutron star would spiral inward through the diffuse atmosphere of the giant, eventually coming to rest at its center. The result is a bizarre hybrid object, the immense, cool envelope of a giant star, but powered not by nuclear fusion in its own core, but by the intense heat generated as material from the giant's interior accretes onto the surface of the embedded neutron star. The outer appearance would be nearly identical to a normal red supergiant, but its internal workings and chemical signature would be utterly unique. Finding one of these within a Quattuordecuple system would be the discovery of a lifetime, a direct confirmation of one of the most extreme outcomes of stellar interaction. As the billions of years roll on, the system will inevitably simplify itself. The relentless gravitational perturbations will eventually provide one star after another with enough energy to achieve escape velocity, flinging them out of the group to become hypervelocity stars streaking alone through the interstellar darkness. Each ejection removes mass and energy from the system, calming the remaining chaos slightly. The end state, after perhaps tens of billions of years, might not be a 14-star system at all, but a much smaller, tighter core of survivors. This final group could be a stable hierarchical multiple, a tight triple orbited by a distant binary, for instance whose orbits have finally been widened and circularized enough by the countless interactions to achieve a true long-term stability. Alternatively, the entire process might culminate in the formation of a single, intermediate mass black hole at the system's center, the product of successive mergers and accretion, silently holding the remaining stars in its grip. The Quattuordecuple system's journey is a grand cosmic saga of chaos and order, a billions of years long story that begins with a fragile gravitational ballet and ends by forging some of the most exotic and powerful objects the universe is capable of creating. As we've journeyed through these 30 astonishing discoveries, it's clear that Quattuordecuple star systems represent one of the most extreme and puzzling environments in our universe. challenging our fundamental understanding of stellar dynamics and opening new frontiers in astrophysics that will keep astronomers busy for decades to come. These 14 star families are not merely cosmic oddities, they are profound statements from nature, demonstrating that the universe's capacity for complexity far exceeds what we once imagined possible. Each system is a grand experiment in gravitational physics, running on a scale and time frame we can scarcely replicate, offering us a front row seat to processes that test the very limits of our theories. They force us to question long-held assumptions about star formation, orbital stability, and even the nature of matter itself, proving that reality, in its most extreme corners, is always stranger and more wonderful than our models predict. The true legacy of these discoveries lies not just in the answers they provide, but in the breathtaking new questions they pose. Every observation seems to unravel another layer of mystery, from the hidden mass binding these systems together to the bizarre chemical signatures on stellar surfaces that hint at violent and exotic histories. These systems are cosmic classrooms, teaching us that chaos and order are not opposites but can coexist in a delicate, dynamic balance that persists for billions of years. They show us that planets can form in the most hostile of environments, that stars can be captured and adopted across cosmic timescales, and that magnetic fields can interact in ways that generate some of the most energetic signals we detect across the cosmos. The study of Quattuordecuple systems is a humbling reminder that we are still beginners in mapping the full diversity of the cosmos, and that the greatest discoveries often come from looking where we least expect to find anything at all. This is not the end of the story, but a thrilling new beginning. The next generation of telescopes, both on the ground and in space, will turn their powerful gaze toward these gravitational marvels, peeling back the layers of mystery with unprecedented precision. We will listen for the faint hum of their gravitational waves, map their intricate orbits in 3 dimensions, and search for the subtle fingerprints of hidden worlds orbiting within their temporary zones of stability. Each new piece of data will bring us closer to answering the fundamental questions these systems raise about the formation of our galaxy, the nature of dark matter, and the very laws of physics. The journey into the heart of these 14 sun families has just begun, and the greatest revelations undoubtedly still lie ahead, waiting in the starlight for us